Here's the end part of 2.1 for APC. I know you can read, so I'll hit pause and read. First part, they want the moles of Cl minus. We know we're using NaCl, so that's a super soluble with Na. It splits completely, so all the molarities that apply to this also applies to the Cl minus alone. If we want moles, well, that's not too hard to get because liters times molarity generates moles. So they want the volume in liters of the Cl2. Okay, well, that's a gas. We can use one of our gas laws because look, they also gave us a temperature and a pressure. And we know moles because 1 mole of this will produce 2 moles of that. So the moles that we just found here, double it, and you've got moles of Cl2. Now we have N. At the front of your booklet on the real test is 3, maybe 4 values for R, 2 of which don't apply to a gas law at all. So be careful. I think there are 4 versions of R. There was a French scientist whose name starts with R, and I don't remember what it was. That's why it's capital R. And they're always constant. You need the one that has the correct units. So like one of them has joules for energy in it. Well, that's certainly not it. What we're looking for, we know has Kelvin and liters, and especially it has atmospheres in it. Don't get the one that has torr in it because we're not using torr here. Put in all your values, solve for V. Then they give us an experiment table for rate. H is already isolated, doesn't change, so let's ignore that. If we compare lines 1 and 2, this is increasing by a factor of 3. By the way, you get a calculator on this, which is important here because doing this by hand is a nightmare. Also, it's really tempting to do this wrong, and I did it wrong for a moment because I was essentially saying that this is bigger than that. Well, no, it's not. And then it doesn't work and things go nuts, right? Also, you get a calculator, so don't bother trying to eyeball this one. Actually, punch it in. This is bigger, so it's this divided by that. We're going from here, it's increasing to here. The increase is a factor of 9 or pretty darn close. They allowed themselves to put in some experimental error. So it's something like 9.022, blah, 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 blah. But we're going to call that 9 because they're not going to ask us to do anything more than that on the real test. I know that somewhere in these workbooks they asked us to do some stuff. We had to use the logs. The real test doesn't require that. They have enough stuff going on. So it's going to be numbers like 9 and 27 and 16, you know, stuff that had, you know, perfect squares and stuff like that. At least when you get down to the other calculations. So we have 3, an increase of a factor of 3 that produced an increase of a factor of 9. So the molarity increasing by a factor of 3 produced an increase by a factor of 9 of the rate. And what is the exponent that governs that? Well, the exponent must be 2, so it's second order with respect to Cl minus. If we use lines 2 and 3, we can isolate the permanganate, and this doesn't change, right? So an increase in the factor of 2, make sure you're going up. Well, it does work if you go down, but then it's kind of a booger. Well, you get, if you go down, you get this is a half, this is a factor of half, and then you get this is a factor of a half. And then you get one, you would get 1/2 to the unknown power equals 1/2. So it does work, but you know, it sounds like making it hard. This is an increase of a factor of 2 going up, and so is this. So we get 2 to the unknown exponent produces 2, and of course it's 1. Now they tell you flat out, it's third order with respect to H. So write out the rate law, you got it. Sticking K, I don't know what that is, but Cl2 was determined to have an exponent, Cl minus was determined to have an exponent of 2. This is 1, and they told you that's 3. So find K, fine. Pick a line, any line, it'll generate the same K. They picked line 1 for because they felt like it. Here is the rate for line 1 and the molarities for line 1. Don't forget to use the correct exponents or you will get the wrong answer. This divided by that, divided by that, divided by that, if you want to think of it that way. And once you notice the pattern, or I've told it to you, you don't really have to mess around with the units. this will be molarity, 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 right? So you'll have molarity to the fifth, but you know the rate needs to be, or it's a sixth, excuse me, right? And you know the answer over here needs to be molarity per second. So what would generate for K, what units would generate that? It'd be 1 over molarity to the fifth seconds, wouldn't it? So this exponent will always be 1 fewer than whatever the sum of the exponents here is. So you don't actually have to fiddle around with it too much. Subtract 1 and stick it on the denominator. So the answer will be, for K, some number per molarity to 1 fewer exponent seconds. Okay, here's a new bit. So reactions, in reality, usually or often have multiple steps. So let's pretend this had 3 steps. If it has more than 1 step, the effect of the molarity generated out of this step that rolls into this step and maybe picks up yet one of the other reactions that wasn't used yet, the effects are cascading and weird and unknowable. It's not predictable by just staring at the net ionic equation or anything. So that's why you have to actually do the experiment. You can't just look at this and say, oh, the rate will be. It just does not work like that, usually. So we do the actual experiment. We run 3, 4, realistically many more tests, I suppose, and see if we get numbers that give us the same kind of exponent. And of course, they simplify these numbers so that the exponents would be stuff like 1 and 2 and 3. So then we come up with a rate law that works and is verified by a real world experiment. However, if it is just 1 step, then the coefficients become the exponents. So if this had 1 step, which it clearly didn't, but if it did, then we would get rate equals K times H plus to the power of 8 times Cl minus the power of 4. But that's not what happened. That's not what happened. So does this have a single elementary step? No, because we did not get the coefficients turning into the exponents. It almost certainly has more than 1 step, and that's why the coefficients didn't turn into the exponents, because the rate law does not match the stoichiometry of the overall reaction. That is a weird way to phrase that. If they ever ask that, I would say because the coefficients did not turn into the exponents of the rate law for the molarities.